All right, let's jump right in. We're about to explore a really fascinating and kind of radical new way of looking at the universe. It's a theory that suggests there's a hidden dimension to reality we've been completely overlooking, a dimension of pure scale. You know, it all starts with this deep, nagging mystery. If you look around, you see it everywhere in nature. Things aren't smooth and continuous. Instead, nature builds things in these very distinct levels, in stable, repeating patterns. Think about it. Electrons have to be in specific energy shells, not just anywhere. Particles come in these neat little families. Why? What is forcing this incredible structure onto the cosmos?
So these aren't those little quirks, they're puzzles that have stuck around for a long time, and our current models of physics really struggle to explain them all from one single principle. But this new theory, it's called the Geometric Scaling Framework, or GSF for short, it proposes something wild. It says these aren't problems to be fixed, they're actually clues, pointing us toward a deeper geometric structure we've been missing all along.
Okay, so let's break down those clues. First, you've got the discrete hierarchies we were just talking about. Why these separate levels of reality? Second, there's this really weird thing called log periodic oscillations. This is where scientists look at data that should be a perfectly smooth curve, but instead they find these tiny, perfectly regular wobbles in it. It's like a faint rhythmic echo in the background noise. And then, of course, the big one, the quantum classical divide. Why on earth does reality seem to play by two totally different rulebooks, depending on whether you're talking about something really big or something incredibly small?
Well, the GSF offers a seriously bold answer to all of this. It says, maybe we've been thinking about scale completely wrong. We tend to think of it as just a parameter, right? A way to zoom in or zoom out on something. But what if scale is a real physical dimension, just like space and time? What if you could literally travel along an axis of scale?
And this is really the core idea, the fundamental shift in thinking. On the left, you've got the old view. Scale is just a label we stick on things to describe them. But on the right, the GSF view says no. Scale is part of the actual fabric of reality. It's a real coordinate on the map. And that one simple change, if it's true, has absolutely profound consequences for everything.
The theory even gives this new bigger arena a name, the geometric scaling manifold, or GSM. So picture our familiar space-time, but now it has these new scale coordinates attached to it. The most important one for us is u. You can think of u as your position along that scale axis. It's like your altitude in the world of sizes. The other coordinates, rho and theta, they deal with things like density and coherence, but it's that u-axis that's the key to this whole ladder idea we're about to explore.
Okay, so if scale really is a dimension, why don't we see things at every possible size? Why are there these discrete levels? Well, according to GSF, the answer lies in a special kind of mathematics, a mathematics that governs stability. It's all about what makes a repeating pattern last and what makes it just fall apart into random noise.
And the secret ingredient for this stability is a special class of numbers called Poisson numbers. Now, you don't need to get bogged down in the deep math here, but the takeaway is this. When you build a repeating, nested pattern, like a Russian doll, using a Poisson number as your scaling factor, that pattern stays incredibly orderly. It just refuses to drift into chaos. They're like natural-born stabilizers.
And GSF proposes that two of these Poisson numbers are absolutely fundamental to our universe. The first one is phi, the famous golden ratio. The theory links it to stability in flat, 2D-like things in spirals. The second one is rho, the plastic constant, which is thought to govern how things pack together in stable, dense, 3D arrangements. So these aren't just random numbers. They're like mathematical attractors for geometric order.
And this slide illustrates perfectly why that's so important. On the left, if you use just any old number to scale a pattern over and over again, it's like making a photocopy of a photocopy. Pretty soon, it degrades into a blurry, noisy mess. But with Poissonal scaling, on the right, every copy is perfect. The structure stays crisp and ordered across countless levels, and that's how you build the durable, repeating hierarchies we actually see in nature. So, let's see how all this builds up into a really powerful picture for this new scale dimension. See, instead of being a smooth ramp where any size is possible, the GSF says the scale axis is actually structured like a ladder.
This ladder has rungs. And these rungs are the specific, discrete levels of scale where those super-stable, Poisson-driven patterns can form. You could say reality just prefers to exist on these rungs. It's where things are stable and can last for a long time. Now, in between the rungs, you have what are called corridors. And this is unstable territory.
Just like you wouldn't try to stand on the empty air between the rungs of a real ladder, physical systems don't like to hang out in these corridors. And that's why we see these distinct levels with what looks like empty space in between.
But then, how does anything get from one rung to another? For that, the theory introduces another new idea: post-scores. You can think of them as these special, hidden pathways, almost like secret tunnels, that offer a stable route through those unstable corridors, connecting one stable rung to the next. So, the process of changing scale suddenly becomes this dynamic journey. A system is sitting there, happy and stable on a rung. When it gets pushed and is forced to change, it doesn't just slide smoothly up or down. Instead, it finds a specific post-score pathway and makes a kind of leap through the corridor to a new, stable rung. This could explain why transitions in physics often seem so sudden and distinct. Okay, so what's the big payoff for learning all this new language about rungs, corridors, and post-scores? Well, the payoff is huge. It's unification. See, GSF doesn't try to replace quantum mechanics or relativity. Instead, it tries to provide a single underlying geometric map that shows how they're all connected. And this right here, this is the big aha moment. Just look at this table. It's proposing that our different branches of physics are really just different ways of looking at this one single geometric scaling manifold. Classical mechanics? That's just what physics looks like when you're stuck on a single rung. Quantum mechanics? Well, that's the strange wave-like stuff happening on a specific rung. And the renormalization group, which is a super important tool in modern physics, that's just the math you use to describe moving along the scale axis itself. They're not separate theories. They're just different slices of the same deeper reality. Now, look, this is a beautiful, elegant idea. I mean, who doesn't love a good unifying theory? But in science, being beautiful is not enough. It has to be testable. It has to make predictions that we can actually go out into the real world and look for. So the big question is, how could we possibly find any evidence of this invisible ladder structure? I mean, really think about it for a second. We can't just take a picture of a rung or a post-score. The structure exists in the dimension of scale itself. So how would it even show up in the data we collect from our experiments? What would be its fingerprints? And the answer brings us full circle, right back to one of our original puzzles, those log periodic oscillations. GSF predicts that these mysterious wobbles are, in fact, the primary signature of the scale ladder. They are the faint echo of the rungs. When you plot your data against the logarithm of scale, you're essentially looking down that u-axis, and the rungs should appear as this regular repeating pattern, a wobble. So the amazing thing is that GSF makes a very specific testable prediction. It says that for basically any physical quantity that follows a scaling law, the real-world data won't be perfectly smooth. It will be the smooth law plus a tiny oscillating cosine term. And the frequency of that wobble is directly tied to the spacing of the rungs, which, if you remember, is set by that piso number 5, the golden ratio. And that gives us a hard number to actually go out and look for. The theory predicts that when you analyze the frequencies of these wobbles in all sorts of data, you should find a peak, a spike, right around 13.05. This isn't some vague, hand-wavy prediction. It's a direct, falsifiable test. If physicists start finding this specific frequency hidden in data sets all over the place, from particle physics to cosmology, that would be incredibly powerful evidence that this scale ladder might actually be real.
So in the end, this whole framework really challenges us to ask a different kind of question. It suggests that to truly understand reality, we need to go beyond just making a list of particles and forces. The central idea is pretty simple, but its consequences are huge. Scale is geometric. And if that's true, it means the most important question is no longer just what is the universe made of, but what is the geometry of its instruction manual?